In this tutorial, we're going to take a look at what are called the special products. And there's two different ones here. The first one is when you're squaring a binomial. So x plus 3 squared means 2x plus 3 is multiplied. And I'm going to model these with some algebra tiles on this page before we get into some just algebraic examples on the next two pages. So this, if you haven't seen algebra tiles before, this is an x because it's a rectangle that's 1 unit in this dimension and x units long. 1 times x is x. These are each ones. There are 1 by 1 squares, so each is an area of 1. So that's why this is x plus 3. This dimension here is also the other x plus 3. It's x long and then 3 more on top of that, so or in addition to that. So this is x plus 3. Now, when I find the area of this whole thing, then these terms are have a graphical representation of what x plus 3 times x plus 3 will work out to be. So if we multiply these together, this is a rectangle, or actually it's a square because the two dimensions are supposed to be the same, an x by x squared. Now, depending on the device you look at this on, this might not look like a square. It might look like one dimension is a little longer than the other, but it's supposed to be a square because these two dimensions are the same. And so this area over here is 3x. There's 3 x's here because it's x times 3, which would be 3x. And the same with this one here. It's 3 times x long, so that would have an area of 3x there. And then this is 9 because it's a 3 by 3 square. 3 times 3 is 9. Now, if we kind of do this the long way, these are how we get the 4 terms. Again, the idea behind these special products is to recognize patterns so you don't have to go x times x is x squared, x times 3 is 3x, 3 times x is another 3x, and 3 times 3 is 9, and then collect like terms. The idea is to see some shortcuts here so that you can do this very quickly, because if you're squaring a lot of binomials, you don't want to have to write out all these terms and some arrows every single time. Now, when you're squaring a binomial, this number and this number will be the same, well, and the x's are as well, because the two binomials are the same. So that means that this term here and this term here will also always be the same thing. And so here's the shortcut. There's actually 2 of these 3x's, and the 3x's come from multiplying the 3 by the x, those two terms together. And the 9 comes from squaring the 3. 3 squared gives you that 9. So 3x times 2, or 3x doubled, is 6x. So again, the idea is to not have to do all this. This is sort of explaining here. That's why I wrote it all out. So x plus 3 squared, x squared is this term. 3 squared on the end is 9. And 3 times x, which is 3x doubled, gives me 6x. So we want to be able to go directly from here to here. This is just, again, a graphical representation to show you that's where all the parts come from. That x squared is this area here. These two things are the same, so there's 2 3x's, that's why that's a 6x. And this 9 comes from multiplying 3 by 3, or this 3 by this 3, that's why that's a 9. So in general, a plus x plus a squared is, and this is kind of like what I'm thinking so that I can write the answer down right away, directly from here to here. So x squared at the beginning, a squared at the end, and this is always a times x doubled. Okay, this ax comes from multiplying the two parts of the binomial together. So x squared plus 2ax plus a squared is what x plus a squared expands out to. Now, the other special product is when the two binomials you're multiplying together are the same, except there's a plus in between the two terms in one of them and a minus in the other. And it doesn't matter which is first. If you want to write the x minus 3 here and the x plus 3 here, it's exactly the same thing. And so when, again, one more area model here, the green means positive, the blue means negative. Okay, so that's what the blue means. So x minus 3 is this dimension across the top, so it's x and 3 negative 1's. Now 3 negative 1's, same as negative 3. And then x plus 3 is the other dimension, so this is x plus 3 positive, so this is x plus 3. So This is an x by x squared, so its area is x squared. This area right here is x times negative 3, so that would be minus 3x's. So there's 3 negative x's there. This rectangular area here is 3 times x, so that's 3x. And then this area here comes multiplying negative 3, so that's negative 3 right there, by positive 3, so that's positive 3, and that's negative 9. Now, if these two binomials are the same, except we have opposite signs in the middle, then this number of x's here and here are always the same number of positives as negatives. So those will always add to 0. A lot of people will say cancel out. Okay, they add to 0 actually. So again, we don't want to have to go through the x times x is x squared, x times negative 3 is negative 3x, 3 times x is 3x, 3 times negative 3 is negative 9, because you see these two terms in this pattern, those are always opposites, just like the opposites in the diagram here. So those add to 0. So you'll see some people do this kind of thing. They go cross out like that. And so the final answer is just x squared minus 9. Again, the 9 comes up from the end from squaring the 3. So that's where we get the x squared minus 9. So when you see this product, this is kind of what I'm thinking here. X times x is x squared, and then minus this times this. See, those numbers are the same. So 3 squared gives you the 9. So in general, if we're multiplying x plus a by x minus a, again, this is the same pattern as here. I don't want to have to write out all these terms, but like that's sort of the long way to do it. So x times x is x squared, x times negative a is negative ax, a times x is an ax, a times negative a is negative a squared. And under this scenario, again, these will always be opposites and add to 0. So the final answer is just x squared minus a squared. So we want to be able to go directly from here to here, because realizing or remembering that those are opposites are always going to add to 0. So let's take a look at some examples on this page, and then I'll go a little bit of a word problem on the last page. So it says expand and simplify using the special products, and we've got a few of each of the examples like the previous page. So the first two are we're just squaring a binomial. So I don't want to have to write out x plus 4 times another x plus 4, write some arrows, write out all the terms, collect like terms. This first line will always be what I'm thinking. Okay, so I would not be writing this down once you get comfortable with this, but this is kind of what you're thinking in your head, because I'm going x gets squared at the beginning, 4 gets squared at the end. And this middle term comes from multiplying this by this, that's the 4x, and doubling it, because when you're squaring, there are always going to be 2 of those identical terms. So x squared plus 8x plus 16. Okay, so again, this is what I'm thinking to get directly to here. X squared is this term. 4 squared on the end is 16. This times this is 4x doubled. It gives me 8x. Okay, so that's how I'm going directly to this answer. Similar with b. Again, this is the line I'm thinking about. This is just in my head. I'm trying to show you what I'm thinking here. So 7x squared at the beginning gives me 49x squared. The x term comes multiplying this by this and doubling it. So there's my 7x times negative 6 doubled. So that's negative 42x. Doubled is negative 84x. And then I'm squaring the negative 6 in the end, which is 36. Okay, so again, trying to go from here directly to here. C is one of those multiplying two binomials that are the same, except there's a minus in the middle of one and a plus in the other. So again, this is what I'm thinking. It's going to be this times this squared, or this times this, 5x times 5x, or 5x squared, minus 11 times 11, or 11 squared. So 5x times 5x, or 5x squared, is 25x squared, and negative 11 times positive 11 is minus 121. So again, trying to go directly from here to here. In D, again, this is a squaring like A or B here. So again, this is the line that I'm thinking, trying to think about in my head. 8m squared is what I'm going to start out with. So 8 squared is 64, and m squared is m squared. This term here comes from multiplying this by this and doubling it, so that's what I'm showing here. 8m times 7n is 56mn. So that's 56 mn doubled is 112 mn. And then at the n, 7n squared is 49n squared. Last one, E here on this page. Again, this is kind of like the C one here, multiplying two binomials, but one is a minus in the middle, the other is plus. So see, this product is negative 9 pk. This would be positive 9 negative 9 pk and positive 9 pk, so they add to 0. So we don't have to worry about the pk terms. So it's really just k times k, or k squared, minus 9p squared. So k squared, and then 9 squared is 81, so this would be 81 p squared on the end. So there's some examples of using the special products. So let's take a look at an example on this last page here. So this is a little bit of a word problem that involves some special products. So we have this oil spill in the lake, and it's in the shape of a circle. So it's kind of like somebody dropped some oil in the lake, and of course it's going to expand. You know, if there's no wind, there's no current, it's going to just expand out in the shape of a circle. So, and of course it's expanding. It's not just sitting there. It's getting bigger, growing bigger until it would get to a certain thinness, and then it wouldn't grow anymore. In A, it says if the spill grows by 5 kilometers in radius, what is an algebraic expression for the new area? So we're not asked to find the area if the radius is 5. We're asked to find an algebraic expression for what the area will be if it gets 5 bigger. So the answer isn't just going to be a number here, it's going to be an algebraic expression. So we don't know what the initial radius is, so we'll call it r. So remember, the area for a circle, area formula, A is equal to pi r squared. So that's the area of the original spill. So we're going to call r the original radius. So an algebraic expression for this new area. So we use the area formula, but instead of r, it's whatever r is plus 5. So that's my bigger by 5 kilometers radius. Okay, so it's 5 bigger than r, whatever r is. So that's what I'm going to expand. And you see, this is one of the special products. We're squaring r plus 5. So I don't want to multiply r plus 5 by another r plus 5 and collect like terms. And again, just like the examples in the previous page, this is what I'm thinking, okay, when I'm going to go directly to the final answer here. So I'm squaring r plus 5, so I'm going to square the r at the beginning, I'm going to square the 5 in the end. This comes from multiplying r by 5 and then doubling it. So to go directly from here to here, r squared is r squared, 5r doubled is 10r, and 5 squared is 25. And then I distribute my pi in. So pi gets multiplied by each of these, so it would just be pi r squared plus 10 pi r plus 25 pi. So that would be a formula for what the new area would be if the radius increased by 5. Okay, so if you said, well, let's say the original radius was 2, and it got 5 bigger, it went to 7. So we could, to find this new area, just put 2 in place of r if you knew what the original area would be, and that will give you what the area would be if it got 5 bigger. In B, it says if the spill grows by 5 kilometers in radius, okay, so same idea as A here, what is an algebraic expression for the change in area? Like how much bigger is the area? So to find the change in area, we're really going from what this area was to what this area was. So the change in area, and the Greek letter delta is often used to represent change in. Delta area, change in area, is the new area, this here, minus the original area. The original area is just the pi r squared. And so notice what happens here is these pi r squareds are opposites. So really this is just the change in area. It's just 10 pi r plus 25 pi. So the area would be 10 pi r plus 25 pi larger. So again, if we went back to the 2, if it was originally 2, how much bigger it would just be 10 pi times 2, or 20 pi plus 25 pi, and we could add those to say it's 45 pi larger. So again, so there's Again, another example of squaring a binomial, and we're trying to go directly from this shortcut directly from here to here. This is really, again, I'm just writing this down because that's what I'm thinking in my head when I'm doing this squaring. And that's the end of the tutorial.